Check. Welcome back, everyone. We start this afternoon session. We have three more presenters today. So first up, we have Bianca Tremblay. She'll be presenting her project vessel this year, and enjoy, as well as our online guests. Thanks.
Hello all, thank you for joining me today. My name is Bianca Tremblay and I will be presenting to you my naval architecture design project, which is a 147-meter RoPax ferry by the name of Hasu. Now, I know that we've all come back for lunch, so I want us all to relax and settle down as I show to you your next vacation destination. Welcome to the Ryukyu Island chain in south of Japan. It is the southernmost portion of Japan, and it is a subtropical paradise with white sand beaches and a rich cultural history. I have to admit, it is definitely a place that I would like to visit myself. Unlike other travel destinations in Japan that are typically accessible by train or by car, this series of island chains is only accessible by air or by sea, which means that the local population, as well as the tourism industry, relies heavily on ferries to get from the mainland to the series of islands. So my mission for this project was to create a vessel that would meet the vehicular, pedestrian, and cargo travel demands between mainland Japan and the islands of Okinawa Prefecture in a fast, safe, and comfortable manner while optimizing profit over the life of the vessel. The route that this vessel will take is the pre-existing Kagoshima to Naha route with stops in 5 auxiliary ports. The total journey is approximately 639 nautical miles one way, and it takes around 26 hours to get from Kagoshima to Naha or from Naha to Kagoshima. So in order to begin the design process, one of the big parts that we had to do was to do a state-of-the-art analysis. And the sources that I used to gain some inspiration for my vessel were the ships that were currently operating the route, significant ship publications of multiple years, and ship data from the Clarkson's research database. And with this data that we collected, we were able to perform parametric analyses to determine the proportions of our vessels. We also used empirical calculations, and we compared these calculations to the pre-existing data to see if we were around the ballpark. So this graph over here shows a length to beam comparison of pre-existing ferries. And as you can see, my ship lands pretty much on the average line of its size for its proportions. And with these types of analyses, we were able to determine the parameters for my ship. So the length overall is 147 meters. It has a length between perpendiculars of 139.01 meters, a breadth of 29 meters, a depth of 14.5 meters to the main deck, a draft of 6.27 meters, a displacement of just over 12,000 tons, a block coefficient of 0.57 meters, and a cargo dead weight of 4,000 tons. The ship's speed is 21 knots, and it is quite fast. It is fast so that it can be competitive with the pre-existing ships on this route. And doing this parametric analysis also allowed me to confirm that having a ship that carries 650 passengers, 44 crew, that has 700 lane meters of vehicle space, and 120 TUs, which is 20-foot containers, or 240 10-foot containers, was a realistic expectations for the cargo carrying capacity of my vessel at that size. The next phase of design was the line development, and I used a lot of parent vessels in order to draw inspiration for my lines. The reason I used parent vessels of the same ferry company and the ships operating the same route is that they have similar mission profiles. So they were the ships that were the best suited for that route. As you can see, my design does draw a lot of similarities from these vessels. I just try to adapt them to have a slightly more modern touch and to, while still keeping like the traditional, conventional line structure of the company ships. So this is my lines plan that I created during the hull development phase. As you can see from the underside of the hull, there are some particular parts that were taken into consideration, especially when it came to maximizing speed and minimizing resistance. I have a very narrow bow with a small half angle of entry, and this is to reduce the resistance in the ship. I also have a bulbous bow that helps to reduce wave-making resistance. And overall, my goal was to guide the flow of water along the hull so that it would flow easily into the propellers in order to maximize the efficiency of my propulsion system. The next phase of design was the general arrangement. And if I were to go through the entire general arrangement, this would be an hour-long presentation. So I will just do a brief overview to give you an idea of where everything is situated. To start off, we have the 2 cargo decks, which include car and container carrying space. They are loaded by 2 stern ramps at the back of the vessel, one on either side, depending on which side the ship is docking. The mission profile and the destinations where the ship was stopping guided a lot of my design because of port restrictions that had to do with pier length and to do with docking side. There are some ports that have very little maneuverability, and so that was a concern. Some ports could only dock on one side. Next, we have the 2 machinery decks, which contain my main engines on the lower level, on the tank top, and the auxiliary gensets on the tween deck just above. There's also some tank spaces for any kind of consumables that the ship may need along the way, such as fuel oil, fresh water, some ballast water, some water treatment plants, and sewage treatment plants as well. And finally, we have 3 accommodation decks. There are 2 decks that are dedicated to passenger spaces and to passenger accommodations. As I said, this is a 26-hour journey, so there is an overnight portion to the voyage, although there are auxiliary stops, so some of the passengers will get off at earlier stops and not continue for the full length of the voyage. But for those that do continue, there are cabins so that they can take a nap in between. And there are, on these decks, a cafeteria, some lounges, there's a childcare facility, lots of great amenities on board. The crew deck has a portion that is separated for passenger access, and the other side is completely isolated to just the crew. The passenger access contains some of the amenities such as the gym, the spa, sauna and change rooms, just some extra amenities to make the voyage pleasant and to increase business. And the crew accommodations are completely separate from that. And of course, there is the wheelhouse top, of course. The next phase of design was powering. So for my powering and propulsion, I decided to do a resistance analysis, and from it, I was able to pick out 2 medium-speed diesel engines with gearbox. They are the Everlens V32-44CR, and to accompany that, there is 1 bow thruster and 1 stern thruster. And this was really important because of the maneuverability aspect of going to small ports in the Okinawa region. One factor that was really important in the design of my ship, because it is a passenger vessel, was the fact that I had to abide by SOLAS's safe return to port regulation. And this meant that for my engine room, I had to have 2 engines that were completely separated from one another by a watertight bulkhead, so that if one engine room became unusable, that there was redundancy in the system so that the vessel may return to port under its own power. So redundancy was always on my mind throughout the phases of design because it was an important component of my regulation for my ship type. Next, I came to my electrical analysis, and I took the expected electrical loads on my ship and divided them into non-emergency loads and emergency loads. And this resulted in my single line diagram. Once again, redundancy was a big factor in designing the electrical layout as well, so that the emergency loads would remain under safe return to port regulation. There would still be power to these important loads so that the vessel could return to port under its own power, and so that necessary systems would remain operational. From the electrical analysis, I was able to select 2 auxiliary gensets with a total required power of 27,886 kilowatts. The total power from my selected models was 2,800 kilowatts, and they are the MAN L2330H Mach 3. I also selected an emergency genset, and the total power for it was 336 kilowatts, and it is a Cumming KTA-19. When it came to the structural calculations, I used Lloyd's Register rules and regulations for the classification of ships. All of my structural calculations were done using mild steel, and my ship is longitudinally framed because of the longitudinal loads that are imposed on it due to the length of the vessel. It is 147 meters, and so it will be subject to some longitudinal bending moments. Some of the interesting portions of my structural calculations that were quite unique to my ship type were vehicle and container loads on my car decks. And this is because not all of the containers that I am carrying have plushies in them. Some of them will carry heavy machinery parts. So I had to design for the worst case scenario of loading conditions on my cargo decks. But I also had to take into consideration wheel loads from vehicles that were rolling on these decks. And those are loads that can create fatigue in the structure. So this had to be taken into consideration in my Lloyd's regulation calculations. So that was a fun little challenge for me along the way. When it comes to my capacity plan, I designed the ship to be able to operate with a 2-week endurance. And I also included a water treatment plant and a sewage treatment plant to help reduce some of the capacities of my tanks on board. So just as a brief overview of the tanks and the capacities, I have 1,101 cubic meters of MDO fuel, 728 cubic meters of fresh water, 401 cubic meters of gray water, and 334 cubic meters of black water. And with the help of the water production plant and the sewage treatment plant on board, this ship is able to be completely self-sufficient for 2 weeks. The capacities that you see over here for fresh water, gray water, and black water are for 1 week. So let's say that one of the treatment plants does go down, we still have at least 7 days of self-sufficiency on board. I also have 4,552 cubic meters of ballast water. And although it is not used that much in my loading conditions, it is still useful to have on board so that we can trim the vessel fore and aft. And if there are some loading conditions in which there is a list to one side, we can help balance it out and ensure good propeller immersion to maximize the efficiency of our propulsion system. As for my trim and stability analysis, I made sure that I was compliant with Transport Canada standards and IMO standards for intact stability. And I made sure to pay special attention to the passenger ship criteria. And so for this, I tested 10 different conditions for trim and stability. This includes a fully loaded cargo condition where I am operating at my maximum dead weight capacity, which is 4,000 dead weight. And I also tested a fully loaded condition where I have my full passenger complement of 650 passengers and a full vehicle capacity as well. So these are my two fully loaded conditions. And then I also tested a lightly operating condition if the ship needs to go for maintenance or repair. And these were tested for port departure, mid-voyage, and port arrival. My worst case scenario condition was the port departure full cargo with 4,000 ton deadweight. And as you can see, it still passed the stability analysis. I also did an analysis of a special condition, which is called the passenger crowding condition. And this is a condition where we envision having passengers being loaded up as high as possible on the ship and over to one side, just as a worst case scenario, because obviously humans move around. Unlike containers, unlike cars that are lashed down, humans do move around on the ship and thus can affect the stability of the vessel. And I was able to pass this condition as well. So that is wonderful. So here are some of the capabilities of my design. I am able to carry 650 passengers with 44 crew. I have a total deadweight of 4,000 tons. I have 700 meters for vehicles and cars. I have 120 TEUs, so those are 20 foot containers, or 240 10-foot containers. I have an operating speed of 21 knots, which remains competitive with vessels operating that route, a range of 6,390 nautical miles, an endurance of 15 days. Now let's talk money. The price estimate that I performed was using the Carriot method, but it was adapted to modern times to account for changes in labor, material, and overhead costs. It also takes into consideration inflation rates since 1975 and adapts it to US dollars instead of British pounds. So assuming that this vessel is built in North America, it would cost around 136 million USD. So this could be yours. However, if you don't have 136 million USD, that's okay. The vessel is intended to be built in Japan, where some labor costs are a little bit less expensive, and there is also a lot more automation in the build process. So the price could come down a little bit for you. We might get a deal. So yes, as some closing remarks, this has been an incredible learning experience, and I really want to thank all of our instructors that have helped and supported us along the way. We couldn't have done it without them. So thank you all for listening to my presentation. It really means a lot. Are there any questions?
Did you have to use a bunch of hoistable decks or ramps, movable ramps?
I do have some movable ramps going from the loading deck to the upper car deck. Honestly, they can stay in their fixed position technically, but if we want a little bit more space, we can hinge them up. And that does provide a little bit more headroom, especially if we have some trucks that are being loaded on the lower decks. Yeah. Yes.
Mentioning you're just looking at your structure.
Mm-hmm.
Did you manage, as you were starting to look at, because your KG was up?
Yes.
And aluminum for the superstructure?
Yes.
How did that result in what's the change?
Yeah, so initially when I did my stability analysis, there were some issues with my center of gravity being a little high. And so in order to mitigate that and improve my stability, I decided that it may be better to reduce the weight of the superstructure by perhaps shifting to aluminum or a lighter weight of steel. And what that did was it lowered the center of gravity of the vessel, and that helped me to pass all of my conditions. So this is something that I would consider for the next turn of the design spiral. I would definitely look at reviewing my structure calculations to account for this change in material in the superstructure, and making sure that it would be adequate in terms of strength as well for the loads that are being carried in the superstructure. Yes, Kevin.
We have an online question from Yang.
Okay. Hi, Yang.
So he says, awesome ferry. Some questions for you. What was a particular aspect of the vessel that made you feel like a real naval architect, and would you do a passenger ship again?
Doing a passenger ship has been awesome, honestly, in some ways, and awful in other ways. I think it's been an amazing learning experience, and I really got to explore some parts of the ship design process that were different from regular cargo ships. So I am really glad that I did do it. Whether I would do it again, honestly, I've done it once, so why not?
And where were really working?
Thank you. And honestly, every part of the process, I felt like I was putting some creativity in it, and that made me feel like a naval architect. Yeah. Any other questions?
Or whatnot. Yeah. I know. No one No, he didn't.
Okay, so I do my stand-up routine and tell some jokes while we have a quick pause. I'll tell you a story, yeah. I know, we're a little ahead of schedule. The next presenter, I'll just give a minute they'll be back.
What's the bird's name?
How many?
Show us that dad step.
No, last time I was on the stage, no. How many do we have online, Kev? Is it just the one, the one troll? No. Thank you very much, Yang. Actually, wonderful questions. We're joking. Here to heckle us. Okay, looks like we have a presenter back now. All right, up next we have Timothy Byrne. He's going to be presenting his design project to you all. So, please enjoy. Thanks.
He had it there earlier.
You can just just click on the mouse if you.
Okay, because I would like to go up there on the stage if possible.
You have to click on it.
Perfect.
I just want to make a note that we have 6 online watching and only game.
Jesus Christ, this is a pain in the ass. Oh, that works. Oh, finally, Jesus. All right. How do I, Kevin? How do I plug this in? Or oh, the thing. There we go. Look at this. Perfect. And perfect. All right, everyone. I would like to thank you all for attending my presentation. My name is Timothy Byrne, and I'll be representing to you my Handymax bulk carrier with a dead weight of 38,000 tons. So what you'll see in this presentation are the vessel's mission and objectives, the vessel key features, hull design, general arrangement, propulsion and powering, electrical design, structure, capacity, trim and stability, estimate price, and conclusion. So the main mission for this vessel is to carry grains between Vancouver, Canada, and Shanghai, China. From Vancouver, Canada to Shanghai, China, it can carry either wheat, barley, or canola, and from Shanghai, China, back to Vancouver, rice. The vessel will be built by Yangtzejiang Shipyard in China, and maintenance will be taken care of by Seaspan in Vancouver. And this vessel will be owned by Alcoa Central. Here you can see in this image the route between Vancouver and Shanghai, where you'll cut through Japan and South Korea to get to Shanghai. This is a 5,063 nautical mile trip. Some of the key features that drove the design is that it's a Handymax size with a range of 11,000 nautical miles, an endurance of 40 days, and a dead weight of 38,000 tons, and some port restrictions as well. The length overall can be either less than or equal to 180 meters, and the draft can be less than or equal to 11.4 meters. These restrictions were in the Shanghai terminals. Some of the other key features is that it is not a self-unloading bulk carrier. The required fuel capacity is 2,016 tons of fuel oil, and it goes at a speed of 14.5 knots, allowing it to compete with other bulk carriers and a fruit number of 0.179. Here is the state-of-the-art analysis that I used, gathering a total of 180 different ships across both Clarkson's research and through significant ships anywhere dating between 2025 to 2015. Here is an example of one of the SOAs here, where there's dead weight versus speed. And as you can see, they all clutter together here near 14, 13 knots, but I wanted to go up to 14.5, so it can be on the upper half of the speed. And over here is another example of dead weight versus speed. And as you can see, there's a very clear trend here where there's a huge line of beam being at 30 meters. So it only makes sense if I went along. So the hull proportions were all designed around those parameters as previously listed. You have a length overall of 180, a length on the waterline of 176.4 meters, a length between perpendiculars of 172.4 meters, a beam of 30, a depth of 15, a draft of 10.6, a block coefficient of 0.82, a midship coefficient of 0.98, and a build radius of 4.85 meters. So here's the hull itself, and as you can see, it flares in quite a lot here in the aft end. There's also a stern bowl, and here in the fore end, you'll notice that I decided to go with the bulbous bow. The reason why is because after researching all 180 ships, it seems to conclude that most, and if not pretty much all of them, go with the bulbous bow. As for which type, I went with a oval to circular shaped bulbous bow because that is best within the crew member threshold and speed that it goes at. Other particular things about it is that it has a long parallel mid-body of 90 meters. This is where 3 identical cargo holes will be located within the parallel mid-body. And as for stern bowl, this is ideal for the shaft arrangement. So that way not too much of the shaft is exposed outside the hull, and that a bracket and bossing will not be necessary. And here is the lines by itself. As you can see, here's once again the stern bolt. This is a cast stern frame. And as you see going through here, you'll see all parallel mid-body that I mentioned earlier. And you can see how the bolt begins to develop here with the bottom lines up here. You can see the shape of the bolt is out here on this station, and the aft stern bolt. And here you can also see the water lines smoothly transitioning into the propeller or the hub of the propeller. And up here, you can see the water line smoothly transitioning into the bulb itself. And here's just a table of offsets. As you can see throughout the middle, you'll see a lot of 15s and 14.99s, further verifying that there is quite a bit of parallel body throughout the middle of the ship. And this is the general arrangement. To walk you through it, here is the engine room with a nice big tall engine, 9 meters. You have a self-launching lifeboat, a provision screen, and here are all the cargo holds as mentioned earlier, with these 3 being completely identical, and the other 2 being smaller, as well as the chain locker and a 4-peak ballast tank. And here's the main deck view of this. Here is where the galley, crew mess, dry store, freezer, and cold store are all located, along with a sick bay, the med store, a waste room, an emergency equipment gear, and a locker room, and a small little bathroom, just to be safe. Here is the tank top view with the engine room itself. You have fuel oil tanks all located down here, as well as the main engine itself, and the shaft has the rudder, an emergency escape, and checker plating 750 millimeters above the tank top. And here's just a close-up of the engine room itself once again. And here's a close-up of the main deck, once again, just showing the layout, as well as and I also forgot to mention the casing is located right here. And here's the forecastle deck with the mooring arrangement, and some bulwark, and 2 sets of stairs to go up and down the forecastle. And here are 2 between decks. This is the second highest to the main deck, and there will be 2 fuel oil tanks here, a control room, ventilation room, storage space, and a boiler room. And here on this deck, you will see a workshop and the location of the generator and the emergency escape continuing on from the tank top. And here are all the accommodation spaces. This is a very generous deck here in particular because you have a crew lounge, a gymnasium, along with a laundry room, a theater, a meeting room. The emergency generator room is also on this deck as well, just because it's practical to have the emergency generator above the main deck. And there are also a couple of heads and a coffee room. And here on deck B, you have all the accommodations, which are very nice and spacious. Each crew member gets 1 room to themselves, and there's a total crew of 14. So the chief engineer's cabin is nice and big. The captain's cabin is also nice and big. And the captain's cabin is on the next deck closest to the bridge deck, which the stairs up to that is right here. And here we have the bridge and wheelhouse top. Up inside the bridge deck, there's a little chart room, small bathroom, and all the navigation equipment. And here's the wheelhouse top with a couple of radars and stuff. So the propulsion and powering for this vessel. So hull drop momentum was used to get a total resistance. And a B350 KJ chart was used to find an optimal RPM, a propeller diameter, a propeller efficiency, and a pitch to diameter ratio. All necessary powers were calculated to achieve a required engine power of 12,271.65 kilowatts. And here is what I mentioned. The number of blades for this propeller is quite the outlier nowadays, but it still works. There's a bar ratio of 0.5, RPM of 120, a propeller efficiency of 50%, a pitch to diameter ratio of 94 or 0.94, a propeller diameter of 6.08 meters, and the engine power is 12,316 kilowatts at 85% MCR. And here is just the specs of the engine itself. It is a MAN BMW S50 ME-8. And here is just how that looks inside the engine room in more detail. Here is the electrical design for the main generator. So I required a power of 314 kilowatts, and the generator that I went with was a 6DE18 with a power of 355 kilowatts, a RPM of 720, 6 cylinders, and a growth factor of 13.1%, which is how much over I had for required power. As for the emergency generator, I needed 29 kilowatts, and I sized a generator called the Kohler 35 EFK OZT with a power of 35 kilowatts, an RPM of 1500, cylinder number 4, and a growth factor of 20.2%. And here are the locations as such. On the ER flight, you will find the genset on the starboard side. And on deck A, you will find the emergency generator here in the middle on the aft and base structure. And here is the single line diagram. Pretty hard to read from here, but you have all the bus bars of 480 volts, 360 volts, 240, and 120 volts. And over here is the emergency bus bar. To give you a close-up of one of these, this is the emergency bus bar in better detail. You have things like the fire screen door or navigation light panels and so on. And here are all the bus bars that are used. One 3-phase 480 volt, one 3-phase 220 volt, one single-phase 120 volts, and one 24-volt DC. And the same goes for the emergency generator bus bar as well. As for structure, I used the Classification Society of Lloyd's Register 2025. The choice of material is Lloyd's Grade A mild carbon steel with a K factor of 1.0. The vessel framing is combination frame, transverse on side shells and longitudinal on the bottom and decks. And the frame spacing is a transverse frame spacing of 1 meter, a longitudinal frame spacing of 800 millimeters, and a transverse deep web spacing of 4 meters, except where there's a bulkhead, to where then it'll be 1 meter away from the bulkhead. And as you can see here, this is the profile on the decks. You can see all the longitudinal spaced out. You can see the girders as well. And here you can also see, once again, the deep webs going throughout, as they're not spaced as much in between bulkhead spaces. And you can also see all the girders and how they crank into the engine seat. Here are all the superstructure decks as well, simply longitudinally framed with some deep webs going through, and 3 girders on each. And here are just some section drawings, a deep web frame showing the corrugated bulkhead and all the longitudinal framing, as well as some lightning holes, and a ordinary frame with the same thing once again, just without the bulkhead. And here are the capacities. Highlighted in green is the fuel oil tanks. Highlighted in a dark blue is the ballast water tanks. Pinks shaded is a void space. And black here is the black water, pretty obvious. And the gray one is the gray water. And here are all the plan views for that. There's also the freshwater in light blue here, the oily bilge here in orange. Or sorry, that's the day tank. The oily bilge tank is right here, and the dirty oil tank is here. And this is a midship section to show how the water ballast tanks look from a section view. And the range for the vessel will be 11,000 nautical miles, 563 nautical miles per point A to point B trip. And the vessel has a required fuel oil capacity of 2,016 tons. This vessel achieved 2,021 tons, only 5 tons over. As for trim and stability, I did 6 different conditions. I did port departure with and without cargo, mid-voyage with and without cargo, and port arrival with and without cargo. And as for regulations that I was to satisfy, I decided to satisfy International Maritime Organization, both 1991 and 2008, Transport Canada TB 10943, and Safety of Life at Sea, SOLAS 2009. And here's just an example. This is my considered worst case scenario, being a fully loaded port departure. And as you can see here, it passes that just fine. Now, as per the estimator's price, the methodology used for this was Carriette's method. It is sort of outdated given that it was 1975, but the numbers have been updated as to 2025 numbers. And it was used to estimate the vessel's price, total initial cost, outfit material cost, machinery plant material cost, steel material cost, outfitting labor cost, machinery installation cost, and steel work material cost. And Carriette's method does have some shortcomings, like I said. The cost outfit machinery are not well devised compared to the other estimated values in this method. And getting an accurate estimate of the labor hours is not as simple as it looks. Using the empirical formulas, all the costs are as such. A steel work material of $1 million or $1.47 million, a machinery installation cost of $862,000, a outfitting labor cost in $2.92 million, a steel material cost of $4.39 million, a machinery plant material cost of $22.8 million, outfit material cost is $15.01 million, and the total initial cost is $58,607,860. This is all USD, just for the record. And the vessel's price is $76,190,218. Now, if this were built in America, this would cost up to $99 million. Now, for the record, this vessel was made to be or perceived as a blank canvas. There's nothing really too special about this vessel. There's no bow thruster, no stern thruster. It's a single screw, fixed pitch propeller with a big engine made to power it and be competitive with other vessels by being built nice and cheap, being able to profit quickly and compete with other bulk carriers. With another spin of the spiral, though, there would be some changes that I would consider. For example, increasing the depth to 16 meters from 15. This would be for a few reasons, considering a third tween deck for more machinery space. More ballast capacity would also be nice. And speaking of adding a third tween deck, like I said, using a manifold system for the bilge ballast instead of the typical loop. It's worth trying, though it might not be the best method, and that's mostly because it's more maintenance friendly. And adding a second genset for redundancy. As for improvements to consider for another spiral, items such as adjusting some of the tank placements would be nice, especially in the aft end where I want to keep the propeller fully immersed. And while that is accomplished in this particular stability book that I've done, it would be nice to achieve that with more ease. Further expanding on the scanning, probably adding more items wherever, like perforated flats, brackets, wherever necessary to continue going with that. And further expanding on the machinery arrangement, adding more items to it and figuring out what else can be done with the machinery arrangement. And achieving the target ballast capacity, something I fell a little bit short on when I was doing my tank capacities. I would like to thank all of you once again for attending my presentation. It was really nice to have you all here. Are there any questions that any of you may have? Yes, Kevin.
Hi, question here from Yang. He said, curious if you could explain why your vessel needed over 12,000 kilowatts of power. That seems to be high for the next ship.
It's just a single engine. That's just the resistance I got, and through going through all the powers and finding deliver power and such, that is the power I came up with for the vessel. It is literally just what it is. I couldn't really give you the best explanation, but there was quite a bit of resistance, right? So that is the engine I had to carry this light. And only 50 kilowatts over the required power to go at the high speed. It's 14 and a half knots. That's probably one of the big reasons as to why I need that. Any other questions?
Ballast capacity, you did note that that was a little less than what single ships were. And so in your mitigation chain that you're going to redo this, how would you manage that? You mentioned increasing the depth.
Yeah, so by increasing the depth, we can have more volume in, like, let's say, the wing tanks, and also just in the aft end as well to add more ballast capacity. I could also raise the tank top a little bit as well to add more ballast capacity as well. Those are just some of many of the options I have to pick from. And some of the ballast tanks would just be bigger, like for example, a 4P tank would go up 1 meter in volume. Any other questions?
Oh, yeah, let me just do that. Here you go. Shane.
You need any help setting up?
That should be good.
All right, perfect. You're not wanting this, are you?
I do. I want it for the laser pointer.
Oh, I forgot about the laser pointer.
If there's any cats in the audience, watch out. She does this every time I turn around. Should have brought her to IT a month ago, but I've just kind of been coasting on. Great. Okay. Come on, baby. Oh, she works. Okay. Great news. I do that. Really happy there was nothing open on my laptop there. Business one.
Are you heckling me? I still grade your stuff.
You do?
Not me. I wrote it in pencil on purpose.
Okay. Are you
I'm
doing
just gonna
the
just a quick
introductions?
introduction. This is Rose. This is Jane. Call me Rose. No, I'm ready to come back here.
It's gonna be like
Okay.
a big show reveal.
Thank you, Tim. We're ready now. So up next we have,
Doesn't like you.
doesn't like me. Up next is Jade Rose. I'll let you do your intro.
Cool.
Thank you.
Thank you, everyone, for being here. I know it's been a long day. Some of you are probably tired and looking forward to getting home. I know I am. So let's get through this. I'm J.D. Rose, Naval Architects student in my 3rd year, and I am introducing to you Takupoti. Takupoti is my ship. She is built specifically for Matson Inc., specifically their Auckland hub. Their Auckland hub is basically the cornerstone of service in the Southwest Pacific, with scheduled service to Fiji, Samoa, the American Samoas, Tonga. It's also the sole/primary provider for the Cook Islands and Niue, which are really small island communities down there, which rarely receive any kind of External support, I think there's only 3 ships really operating those routes, and they're all owned and operated by Matson. For the purpose of this academic exercise, I decided that one of those ships is needing to be replaced. So that is the ship I'm designing for today. The vessel criteria set out by the owner are fairly simplistic. Has to be a general cargo ship capable of carrying multiple different types of cargo. 10,000 deadweight, must be able to maintain 15 knots of speed consistently. 630 TEUs. You might notice the 2 asterisks next to the TEUs. That's going to come in later. It's a little surprise, so hold on to your shorts. And she was also required to be self-unloading. Uh-oh. There we go. Great, so this is my route. The route is a circuit of basically all my current bucket list destinations. A bunch of beautiful island atolls, nice sandy beaches. It's about a 21-day circuit, leaving from Auckland, New Zealand, sailing up to Fiji, down to Tonga, another stop in Tonga, out to Niue, the Cook Islands, couple stops here, up to the American Samoas, then to the better Samoas, back down to Fiji, and down to Auckland. Like I said, it takes about 21 days total. This 21 days is not all transit. Some of it is imports, doing loading and unloading operations. So the primary cargo being carried, it's primarily outbound from Auckland, delivering containerized goods, break bulk, vehicles, construction materials, food supplies, medical supplies, basically anything that these small economies really need to rely on. And on return, they're shipping out empty containers. Notice again the 2 asterisks there. You'll be shocked. It's going to be cool. There's also some small exports, fish, sugar, agricultural products, but these only really make about 10 to 20% of the return cargo. So we're really focusing on those empty containers. Why? Why did I choose a general cargo ship? Well, that's what the route needed. Why did I choose this route? Simple. WAPs. You might be asking yourself, what are WAPs? WAPs are wind-assisted propulsion systems. A big part of my mission profile is the integration of wind-assisted propulsion. My passion lies deeply within the sailing world. I'm a bit of a tree hugger. But green initiatives are a strong motivator, and I really wanted to try and integrate that within my project to keep me going. The Polynesian Triangle maintains strong, consistent winds. But just beyond that, I wanted a good, solid, defendable reason to pick this route. And New Zealand's emission reduction plan seemed like a good fit. New Zealand's emission reduction plan covers a bunch of different sectors, including transportation, where they're trying to cut emissions by 41% in the entire transportation sector by 2035 and be net zero by 2050. And there's also a bunch of government incentives for building new types of ships that might have green initiatives and green powered systems. So that's kind of the angle I went with. Yeah, so let's continue. MySOTA, so state-of-the-art analysis. It's been covered by most of the people here today. I think at this point, you know kind of what it is. 75 to 80 vessels, nice deadweight range. Those were the key parameters that I kind of looked at to establish my hull proportions. Here are some of my SOTA graphs. You can see my deadweight versus displacement had a really strong, consistent correlation. So I kind of just picked a number there and rolled with it. Deadweight versus length was a bit more scattered, but I rolled with it as well. Got a bunch of reasonable ranges. There were a few problems with my SOTA, a lot of missing data. Specifically, I had a lot of ships that had a block coefficient, but no displacement, and a lot of ships with a displacement, but no block coefficient. So trying to get the deadweight or displacement versus block coefficient relationship just kind of didn't work out. But I used empirical kind of values for my block coefficient and developed from there. There's also a few wind-assisted vessels. This is kind of a new technology, even though it's an old technology. Not a whole lot of data on new wind shipping initiatives. So that was kind of tricky to see if there was any special design parameters I needed to fit into that category. So I was kind of just going off of vibes. Proportions, these are the proportions I settled with. Overall length of 120 meters, beam of 20.1. The beam was developed to fit within the range of the L over B soda stuff, but it was also calculated using an empirical formula based off of containers and the amount of containers you can fit aboard ships. I kind of wanted to design around containers to have everything fit nice and neatly and just be packaged in a nice little bundle. Draft of 8.31 meters, depth of 12 meters, block coefficient settled on 0.72, displacement almost 15,000 tons, dead weight 10,000, design speed 15 knots, bunch of numbers. If you want to dig into where I got these, you can come find me after the presentation. I'm happy to kind of go through my whole soda and everything. There's a lot of numbers if you're into numbers. Here's my lines plan. I somewhat stupidly decided to not have a parent hall. Design is something that I really enjoy kind of just playing around with, especially with new software, just seeing what I'm capable of doing and seeing if I can fit within the parameters in a way that also satisfied my own personal aesthetics. So there is a couple issues with the lines plan that I'll point out now. These little turn of the bilges here are a little tight. I'd like to round those out a little bit, would help with construction, smooth it out a little bit. I am happy with my water lines. I have a nice smooth water line here with very little forward shoulder. Made me nice and happy. The shear line here is completely aesthetic. The deck, in fact, has no shear. It's just straight across. But I'm a romantic. I like curves. I like my boats like I like my macaroni. Nice and curvy. But yeah, if it was a real build, you probably wouldn't have. It's basically just an exaggerated bulwark, but I think it looks nice. And when you have to look at this ship every day for an entire year, it's nice to enjoy what you're looking at. So, Ian, that's my excuse. GA, fairly simplistic. Engine room aft. There's a forepeak up here. You have 4 cargo holds. Forward one's a little shorter, carrying some 10-foot containers just to get some actual space up there. 2 cranes for self-unloading operations. Nice line of sight going down there. I tested it. I swear it's good. The line of sight is good. It caused me a lot of issues, especially with the kind of wind-assisted propulsion angle I was leaning into. You want a lot of deck space so you have smooth wind inflow to actually get that propulsion. I'm not sure if you can tell from my drawing, there's not a whole lot of deck space. More on that later. Here's my plan view. And here is a lot of the kind of accommodation amenities. You have your stores, galley, mess, MCR is down here. There's a gym. There's some more stores for machinery parts. You can see the arc of the crane swings, chain locker up front, all pretty standard stuff. Here are some of my accommodation decks. So this is my B deck. This is my C deck. Here you have just regular crew quarters. Each crew gets their individual room. They're spoiled. I had the space for it. Captain gets a double bed, so does the chief officer, nice big lounge area. So people won't be complaining, hopefully. If they are, it's probably because I did something wrong. Here's my bridge layout. There's a little electrical room here in the corner. 2 methods of egress on every floor, both internal and external. If I were to redesign my GA a little bit, I'd want to move my stair tower more central. I realized if I have a fire in my casing, the 2 methods of egress kind of both get blocked off at the same time. not ideal. So next turn around the spiral, I want to focus on moving things around a bit. Powering. So like everyone else said, powering was done in NavCAD. I uploaded my Paul model into NavCAD, ran some tests, spit out a total resistance of 431 kilonewtons. It also spit out 420 and 415 and 460 and a bunch of different values every time I ran it. So I settled for one of the kind of average values and went with that, but just know that my confidence in these numbers is not 100%. Gave me an effective power of 2,486 kilowatts. I had a really efficient shaft. You'll see later. My shaft is quite short, which allowed me to not have too many inefficiencies caused by shaft bearings or gearboxes. So my total brake power is only 3,272 kilowatts. Using this, I got a prop diameter 5.3 meters, 3 blades, and 63% open water efficiency, which I was pretty pleased with, especially since I was trying to go with the efficiency fuel savings angle. So my initial engine selection was an Everlance 6S40MEC 9.5, holding 3,333 kilowatts at 80% MCR, 110 RPM. I selected this engine because it had a really, really low specific fuel oil consumption. Again, I'm trying to save fuel. But I did decide to switch to a diesel electric plant later on down the design spiral. I kept the 110 RPM just because that's what my propeller was sized off of. So I stuck with that. And using that, I sized a ABB AMZ 1250 synchronous motor with output of 3,400 kilowatts. I switched to diesel electric specifically because of the wind assisted angle. If you're sailing in windy conditions, you get a lot of gusts. Your thrust doesn't tend to be consistent, so you get a lot of load fluctuations. I wanted to be able to kind of adjust my propeller RPM without having to operate my engine at not optimal speeds. And the diesel electric really helped me kind of figure that out. So my generators are constantly running at optimal 85% MCR, feeding into my engines, allowing for maximum fuel savings, hopefully. We'll see. Here's my engine room layout. I'm not too happy with this one. I feel like some systems knowledge Michael could have definitely given me some insight. I kind of just organized things by function and stuck them in separate rooms, but I really do want to kind of, like Michael was talking about, model it in 3D, see if there's any conflicts, actually see how all the piping is routed through it. Because when I look at this, it's just a bit of a mess and I want to know how to make it better. Structure was done using Lloyd's Classification Society. All the steel is grade A steel, kept it nice and simple. She is longitudinally framed in the midships region and as far forwards as possible and as far aft as possible. But I do have a lot of shape forwards and aft, so I did switch to transverse framing there. In terms of longitudinal bending, I do have large hatch openings, so longitudinal bending was a serious concern. I sized my torsion box stiffeners based off of classic Lloyd's, and after doing a longitudinal bending calculation and finding my hull girder section modulus, I found out that my ship was bending in two, which is not ideal. So I ended up having to beef up a lot of the structure within my torsion box. These stiffeners here were actually turned into built girders. The shear strike plate was thickened up a bit, so was the internal plate here, as well as the deck plate along the torsion box. And after beefing up all that structure, I was managed to pass my longitudinal bending calculations. Yeah, here's structure for my accommodation decks. This is my tween deck, MCR, steering flat. This is just a stringer deck. Looks about the same. My tank top, I did make a different sketch for my tank top that does include a a duck keel instead of just a single line keel. I wanted the duck keel to really offer up space for all the piping. Mike, thinking of you. Between my ballast tanks, I do have these void spaces here that was intended for piping, but as you can see, they don't kind of go anywhere. So having a duck keel down the center to kind of route everything back is something I'd like to do for my next turn of spiral. Capacities, the range was 5,400 nautical miles with an endurance of 21 days. The fuel is calculated based off the range, speed, and the established operating profiles. Gave me a total capacity of required capacity of 792. I got 883, so I have 90 extra tons on there. Ballast was measured off of SOTA data, as well as comparing it to the ships currently operating the route, seeing how much ballast they needed to counteract the light cargo loads, and then all my miscellaneous ones. I did have to increase my black water and gray water capacity because my freshwater capacity was so much higher, so I had to account to make sure that all that additional freshwater was actually going somewhere. Capacities, here you are. Trim and stability, I think is probably one thing I struggled the most with. I followed TP 7301, also known as IMO intact stability. It's basically the same code. I followed general criteria. There were recommendations for container ships, but they were labeled as recommendations, and I'm technically not a container ship, so I didn't exactly include them, but I do want to take a look at them in the next turn of the spiral. All my conditions failed loaded, which was not ideal. My max VCG starting off is relatively low. It's below my design draft, and that was a little concerning to me. And I kind of had to deep dive to figure out why that was. Y'all remember the asterisks? Yeah. So 630 TEU is in fact the nominal capacity, which is basically the amount of slots available on the ship to carry containers. However, if you load those 630 TEU with an average homogeneous load, the ship flips over, which means she's not entirely designed to carry loads up on her deck, but that does kind of line up with the ships currently operating the route. A lot of the research I've done has shown that a lot of these ships aren't typically carrying a lot of cargo on deck, but they are carrying a lot of empty containers back on deck. And once I made my GHS data kind of match this, everything passed. And that was pretty cool. So loaded capacity is about 400 TEU, which means I'm able to keep most of my containers down in the holds and not up on deck. So this is my worst case condition, loaded port arrival. Cargo is maxed out, fuel is at 10%, consumables at 10%, waste at 98%. Some ballast added to account for lost fuel and to optimize the trim a little bit, but she passed. So she float. All right, so design capabilities. My mission, I got a general cargo ship, check. She's 10,000 deadweight, check. She goes 15 knots, check. 630 TEU, asterisk, check. She's self-unloading, absolutely. Well, you might be asking yourself, well, Jade, you keep talking about wind-assisted propulsion, but I don't see any sails on your boat. And I'd say you have a discerning eye. You're quite right about that. However, WAPs? Absolutely, we got WAPs. Back to the loaded TEU capacity with 400 TEUs loaded in the holds. We got a lot of extra deck space freed up, which means we can install some sails on there. But obviously they need to be modular because we need to remove them when we load up those empty containers. So look at that. Wow, containerized sails. So as she sails from Auckland, these are loaded onto deck. Typically 2 or 3. They come in either 20-foot or 40-foot variants. Each one is said to save about 5% in fuel. They boast up to 25% in fuel reduction, although I don't really believe that. I think that's just the fancy number. Average about 10 to 15% in fuel reduction. It's plug and play autonomous operation. You just lift it onto your ship, lash it down, press a button, and she's good to go. Which almost seems like an afterthought, but I swear this was part of the initial design. I also looked at the Air Sea Wing, which is a giant kite sail, 1,000 square meters. Also boasts up to 25% fuel reduction, and it's bow mounted and sails up way up in the air, so you don't really have to worry about your container stacks. I would need to move my mooring arrangement down into my forecastle deck to be able to actually fit this on there, which might affect my floatable lengths because I did in fact need my forecastle volume to pass my floatable lengths. So I kind of put this one on the side burner for now. But yeah, WOPs, we got them. So mission, satisfied. Cost estimate, the initial SOTA estimate gave me a cost about $15.6 million USD, built in Chinese shipyards. And then I went through the Carriette method estimate and got a final price of $36 million USD. There is a decent amount of discrepancy between these two values. I think the main reason was the value I used in the Carriette method for shipyard productivity was on the conservative end, whereas Asian shipyards tend to be a lot more efficient, so it should have been more on the other end. But yeah, I'll be somewhere in the middle. Improvements, God, the more I look at my boat, the more I want to change. It's probably part of the design process. I feel like as I'm working on all these projects, I'm learning so much more about the design spiral and all these different design aspects and how they all tie together. So the more time I spend on it, the more I want to change, and it's been a bad rabbit hole. But yeah, there's mistakes within my scantlings, a couple omitted girders and stuff that y'all probably didn't notice, but I'm too honest not to tell you about it. I do want to put more care into the engine room layout. As I was saying, I want to have a chat with Michael about proper systems design and make sure I'm designing the space efficiently and also in a way that makes it enjoyable for marine engineers to just run around down there and have a good time. Cargo hatch layout. I probably redesigned my cargo hatches about 16 times. Still not happy with them. Same with my general arrangement. I think there's about 22 versions of my GA right now. All of them have some kind of issue that I don't like. So it's really hard trying to get everything right. So I put a quote here just for my own personal sake. Makes me feel good about myself. Good judgment comes from experience, and experience comes from bad judgment. I don't know who Rita Mae Brown is, but she sounds pretty wise. And that's my presentation. Kevin.
I got a question from online.
Yeah, Yang, hit me.
I'm
ready. What?
Oh, wow. Was there any consideration towards using alternative fuels such as methanol or LNG powered ship as opposed to bus?
I did look into alternative fuels. However, the actual machinery associated with that is still very expensive. And there is not a whole lot of LNG infrastructure in and around New Zealand. Because I am a sailor, I was also a bit biased towards wind propulsion. It's really what brought me to the school. I love to sail. I want to see more sails on ships. And so I kind of finagled my mission profile to work a bit in my favor, but there was some consideration. I just decided it wasn't the best course for my project. Hey, Mark.
Those wind sails and containers.
Yep.
I've seen these. Do they have storage capacity in them? Like
No,
battery capacity,
so
or is it
they're integrated with the ship, so you actually have to plug them in once they're lashed in. The entire container is storing the sail itself, and then it will fold out in good winds. If the winds become too heavy or turbulent, they'll fold back in to keep themselves safe. It's fully autonomous. They do all the wind angle adjustments, all the weather tracking itself. It's a very cool system. Yeah. Kevin again.
All right, question from Yang.
Oh, there we go.
What was the design decision to place the superstructure position a good distance away from the last row of containers?
Well, that's an easy one. I have pontoon hatch covers. So that little landing area is so I can remove my hatch covers with my cranes and place them there during loading and unloading operations. Come on, Yang. Any other questions?
Stability.
Stability. Yeah.
In terms of mitigating the issues.
Yep.
Containers. Next term, what would be one approach?
Obviously, the approach we all want to hear is a bunch of permanent ballast in the bilge. I could have made my superstructure aluminum. That's always an obvious one to lower your kg a bit. I do think my beam was a little small. I think making her a bit wider, a bit more initial stability would have helped with that. Slightly higher freeboard as well would have helped with my limiting kg. So a bunch of things I could have done that I did not do.
So I just, on that, the freeboard is the one I was angling at.
Right.
Because that gives you our reserve warranty. But the issues you talked about earlier with the sail and you'll stick another tier of containers.
Yeah.
Below.
Very true.
So that reserve points would be huge.
Yeah.
Cheaper than the intelligence or reserve points that the kg.
Appreciate the insight. Thank you. Anyone else? Hit me.
With that absolutely stunning shear line, why didn't you give it a bow split?
I did.
Oh, excellent. I didn't see those lists.
There is drawings with her with a bowsprit. Unfortunately, there was no purpose for the bowsprit, and it was omitted. Just like my bowsprit. Any other questions? Why are you face palming, John? All right. Well, thank you, everyone, for coming out. Big round of applause. Thank you, Ian, for setting everything up. I'll give you the reins. It's all you.
Thank you, Jade. Always entertaining. Do not disappoint. That concludes our presentation today. Thank you, everyone, for coming. Those online, Yang, and anyone else. Appreciate all the feedback, and like I said, it's been a pleasure to be a part of this and have you guys for the last 2 years, technically, going through the process of teaching you how to design chips and whatnot. I've enjoyed it. I hope you did as well. So what I would ask for you guys, we're gonna quick debrief in the classroom, and I'll just give you a rundown of a few other things before the end of the term. And for everyone else, thank you much for showing up, and we'll see you all next time. Thanks.